Okay, when we obtained the conduction equation, we hope we can solve it. When we want to solve the conduction, certainly we have to give some clue to the boundary conditions. We know the conduction equation like this. But how to solve it? For special conditions, coordinates, this equation tells us is a second order equation requiring two boundary conditions. For time coordinates, the equation is a first order equation. So we only requiring one initial condition. So Txyz0 equals T0 xyz. We only require an initial condition. So together, for solving this equation, we require two boundary conditions, one initial condition. Okay, let's discuss the kinds of boundary conditions. Because we need two boundary conditions, so we have to discuss different kinds of conditions. First kind of boundary condition. The temperature in the boundary is given directly. Here, this boundary condition is simplest because directly give us the temperature. For example, we discuss this body, we know in the boundary the temperature TW1 and TW2, we understand, we know. In the program, for example, tell us when tau larger than 0, T at the boundary x equals 0 equals F1 tau. Directly tell us the temperature. If the temperature at the boundary keeps in constant, it's more easy. In this case, F1 tau equals constant. So this kind of the boundary condition, we can call it first kind. The second kind of boundary condition, the heat flow density at boundary is given. For example, we discuss this system, this body. The program tells us the flow density QW is given. Just to say, minus lambda partial T partial X at X equals 0 equals F2 tau. Sometimes F2 tau, function tau, equals constant. In this case, we can call it is the second kind of boundary condition. If the boundary insulated, no heat transfer. So the constant is 0. Just to say, partial T partial X at X is 0 equals 0. This kind of boundary condition is simple. Maybe easy to calculate. Okay, the last one is the third kind of boundary condition. In this case, the program does not tell us the temperature, does not tell us the heat flow density, but it tells us the transfer coefficient and the temperature of the fluid outside the fluid is given us. For example, minus lambda partial T partial X equals alpha T minus TF. The conduction equals convection. At x is 0, x is 0 at the boundary. In this case, Tx is 0, and the partial t and partial x at x0 is I unknown. Just is a balance and heat transfer balance in the boundary. At the boundary, also on the boundary, the conduction in the body equals outside the convection. Okay, here is 3 boundary conditions. The 3 section is transit conduction in one dimension. Because 3 dimension is very difficult to discuss, very complex. But here we only discuss 1 dimension. As we know, general temperature distribution in heat media is about T function x, y, z tau in transit conduction. Certainly most cases like this. For transient conduction, the temperature field will change with time, tau. Always is relation to the tau. If the heat flows only in same direction, then the temperature field become only one space dimension. So T equals T function x and the tau. Tau is time. Infinite slab, the equation becomes for very big the plate slab. So the equation becomes partial t partial tau equals lambda over rho Cp power t power second partial x power second plus Q point over rho Cp. This equation is only for one dimension system. Infinitely long cylinder is very similar. Applying energy balance to an element sheet of thickness dr, we also have rho Cp 2 pi r dr partial t over partial tau equals Q point 2 pi r dr. Here is the volume minus partial q partial r dr. We obtain this equation for large cylinder. The equation can be changed to this equation. Finally, we obtained a simple shape 1 over kappa partial t over partial tau equals Q point over lambda plus partial t power second over partial r power second plus 1 over r partial t over partial r. We obtain this equation. This equation for infinite lamp. This equation for long cylinder. Okay, for a simplest example, one dimension steady state problem, if the system is not relation to the time, it is steady state. The equation becomes more simple if also no internal heat generation. So for very big the plate for a big lamp, the equation become partial t power second over partial x power second equals 0. Here is for no internal heat generation. The equation becomes this, just come from Fourier's law. The heat flow is Q equals minus lambda partial t power x equals constants. However, for unsteady state problem, because partial t power second over partial x power second is not 0, because it is unsteady state. So this equation is not constant. So we have to do some solving process. If there is no internal heat generation, the general equation become simple. Only two terms. Partial T partial tau equals kappa partial T power second over partial X power second. This equation, just look, is very simple. But when we solve it, certainly there is some difficult. But this equation is not so more terms, also is very typical. The equation can be solved using the separation of variable method. Generally, the solution can be expressed as like this. T equals one term, two terms together. Here is very typical because this equation is very typical. So the solution also generally we easily obtained by mathematics. Here, rho C1, P, C2 are the integrating constants. So determined by the boundary and initial conditions. So we use the boundary conditions and initial conditions. We can calculate C1 and C2 and P because they are integrating constants. Okay, the fourth section, conduction of an infinite slab with source. Q point is not zero. So in this case, become more difficult to solve it. If the heat source is uniform, Q point is constant, the problem becomes more simple. We can obtain one-dimensional steady state equation as this equation: dt power second over dx power second plus Q point over lambda equals 0. In this equation for conduction of infinite slab with source, the source is constant. This equation certainly can be solved. The solution is T equals minus Q point over 2 lambda times x power second plus C1x plus C2. We know C1 and C2 is integrating constant. They can be calculated by the boundary conditions. No initial condition, because this problem is steady state. Here is a very typical example. Know when T1x is 0 equals T1, the first kind of boundary conditions. Tx equals L equals T2 also is first kind of boundary conditions. So the integrating constants can be obtained as C1 equals T2 minus T1 plus Q point over 2 lambda times L power second over L. Also, C2 equals T1. In this example, finally, we can calculate the temperature distribution is like this, very long, 3 terms together. Here is the temperature distribution in the lab. So this equation is typical. Based on the temperature distribution, the heat flow density at X can be calculated by this equation to calculate the heat flow density. Okay, the heat flow through a cylinder with source like this, but in the cylinder there is some heat source. For infinite long, very long the cylinder, the general equation is this. Also is unsteady state. If the heat flow rate is steady state, in this case, partial T, partial tau is 0, so the equation become like this. It's not so difficult. But including 3 terms, solute the equation, get TR equals Q point over 4K R per second plus C1 ln R plus C2. C1 and C2 is integrating constant. Okay, thank you very much.